Hi. So in this video, we'll look about Monte Carlo Epsilon greedy approach, which is also part of reinforcement learning. And yeah, the problem that we have to solve is again the warehouse navigation using Monte Carlo, where we'll find the best path. Moving further, here if you see, imagine yourself to have a grid like this, where the start position is 0, 0, and the robot needs to find the best path and reach the destination 7, 7. The warehouse has been represented in the form of zeros and ones, where zero represents the free space and obstacles are represented by one. Start and destinations are given 0, 0 and 7, 7. The possible moves are represented with the tuples up, down, left, and right. Now let's study a bit about epsilon greedy approach. This is a balanced approach where epsilon represents the randomness, basically the random moves that a robot can take, and exploitation is the greedy moves which the robot can take on the basis of the rewards or the Q value that it will see, right? If it is going to state from state A to B, up, down, left, or right, wherever, based on the action it takes up, down, left, and right, it is going to get a reward. Wherever it gets the maximum reward, it will go towards that, which is the greedy, and epsilon represents the randomness, the random paths that it is going to explore. Q values represent the expected reward that you get when you move from state A to state B, and it is a dynamic value. The more that particular path is taken, its value gets keep on changing. Reward system for taking a move, whatever you take, you will be given a point -1. If you reach the destination goal by taking that path, you will on the destination arrival you will get a 100 plus points. Backtracking, if you go from state A to B and from B there are no moves possible, that means you can come back to A and take another possible alternative path. That is backtracking. These are the basic implementation details. Nothing has been added much. The learning rate, alpha, the discount factor of gamma, these are the things that have been taken here. We will study about it. And now we'll go to the code walkthrough. So this is the code that we have, the basic libraries that are required. Pi game is used for playing a sound. If in case the robot is stuck, the grid is represented with 0 and 1, free space and obstacles here. Start and destination explained in the PPT. They are similar. And learning steps, we have taken 200 learning steps. So a number of simulations is 10,000. It is better to keep higher simulations so that you get the best possible path. If your number of simulations are going to be lesser, that means the decay rate will also not reach like to the minimal. And so at the end, basically the objective should be the robot should never stop to learn. That means keep a minimal part as random, but also exploit whatever has been learned. So that is the overall idea. Initial epsilon value, that means initial exploration rate, the randomness would be 100%. Minimum epsilon value, that means we want to keep towards the end maybe 10%. Decay rate is indicated by 0.99. We will come to know about this later. Alpha, so this is your learning rate. If your environment is very dynamic, keep the learning rate as higher, 0.5 to anything greater than that. For uh, static environments, for instance, this kind of a grid, keep it very small, zero point 0.1 to you 0.01 to zero point 0.1, anything is okay. Gamma represents the discount factor. Basically, imagine it like if your immediate states are very important where you want to reach, like from cell A, B, C, D, E, if they are important, then consider immediate rewards. But if your end state is more important, keep the higher value higher. For immediate states, keep the gamma value as low. For higher states or future rewards, keep the gamma as higher. Move penalty, for each move taken, -1 will be given. On reaching the destination, 100 points will be given. What we do here in this part, we are pre-computing the moves with respect to each cell in the grid. So how it is? So only the valid moves have been calculated. For instance, if you are at the location 0, 0, you can either go down, which is represented by 1, 0, or you can go right, which is 0, 1, because you cannot go up or left, which will take you out of the grid or towards the wall. So those moves are not possible. So here we are calculating all the possible moves and representing here. Now let's look at the implementation of Monte Carlo. So we will look from the part where we are calling the method. Yeah. So we are passing the warehouse, the start and end destinations, and the number of simulations, which we have initialized as 10,000. Now, best paths or shortest length is there are no best paths because nothing has been done yet. So shortest length has been taken as infinity, so that we keep on changing the shortest paths by keeping the default path as very large. Path progressions, the current path that the robot is taking, and attempted paths, whatever gets attempted. Now here we will look at the queue. So this is the most important part where on taking the actions what reward would be given. So we initialize the queue values with all zeros. So now let's look how that is. So this is the representation of the grid. It's a 2D array. Now for each cell, for instance, this cell would have four values associated with it, right? Some reward, basically up, down, left, right. Initially everything we are taking as zero, but for 0 comma 0, this value you take this up, down, left, right, basically four rewards. For 0 comma 0, this position, which is 0 comma 1, you have these four values. Similarly, for this 0 comma 0, last one, you have this. First is like down, left, up, down, left, and right. So these are the values. So this is your 3D array. And for each of the row comma column, whatever four possible moves are, they are represented with the help of a queue. This queue is updated dynamically once you take an action, or once the robot takes an action to go from one state to another. Moving back, now here we have the learning steps, which are 200. Current best path, nothing has been done. Current shortest is also infinity. Now we look at the epsilon rate, or basically the randomness that we want to have in the program. How much randomly the robot should explore. Let's take, so the formula that we are taking is minimum of epsilon, initial epsilon. So minimum epsilon was zero point 0.1, maximum or the initial is 1, decay rate is 0.99, and iteration. So when you are going to start the program from iteration 0, you are going to have epsilon value as 1. That means 100% random moves will be taken. As you are into the program, your decay will happen, or the epsilon decay will happen, that suppose after 50 iterations, only 60% of the moves will be random, and 40% of the time the robot is going to exploit or make the choices, the greedy moves, on the basis of the q values, where it will say, if I take left, right, up, down, whichever is giving me the maximum reward, I will take that path. So which is the greedy part of it. As you are like towards the last iteration, yeah, you will see the minimum decay rate we will reach is 13%, because we never wanted anything below to go below 10. The reason for this is, if you have only the static moves, then the robot will stop learning, and we do not want that. It should be able to take random decisions as well, or should learn with respect to taking random moves also, but we still want to exploit whatever the best paths are available. So this is the reason for having random greedy, epsilon greedy. And here we have the simulations divided by number of steps. So this part is basically doing the simulations. We start by giving the path as start 0 0. Current position also remains the same. If your current position hasn't reached the destination yet, what we do, we obtain the valid moves. So valid moves for position 0 0 will be these two, 1 0 comma 0 1. So we obtain those, and from, if there are no possible moves, then what you do, you backtrack, basically move to the previous position and pop the move that was taken. If not, still you are not able to proceed, then you have to play a sound that the robot is stuck. Moving further, here this random dot random is going to generate a number anything between 0 and 1, and you compare it with epsilon value, the initial epsilon value for 0th iteration, which will be 1. So obviously this would be left lesser, and we will be choosing a random move. But yeah, and based on this random move, we will be making other choices. Now let's suppose you have taken a random move, and here you, what you do, you, so there were two moves possible, either you go down or you go right. Now on the basis of this, we update the previous position, the current position, and append it to the current path. We obtain the move index. Move index is basically wherever we have moved, up, down, left, or right. Now based on that position, we will try to obtain the reward. Reward would be penalty of -1 if you haven't reached the destination. So of course it would be a penalty of -1. And then we look for future. What would be the future? Basically, if you are in from 0 0, you have reached 0 1, or maybe down 1 0, what would be the maximum reward from that position that we will be obtaining here? And then we will try to obtain the value, or update the value of the previous position, which is q 0 0. So the formula that we use is coming from the Bellman equation. It imagine it like you are at position 2 comma 2, and your robot takes a move which is 2 comma 3. That means it is going right. So whatever the value you have in the current state, obviously we initialize with 0, which is okay, plus alpha. Alpha is your learning rate. We have taken a value of zero point 0.5. Fine. Reward R is -1 into gamma. Gamma we taking as zero point 0.9 gamma times the next state value. So wherever we reached initially is also having a 0 value. So 0 minus the previous state, the value where you are coming from, that one. So this way, if you go from Q2 comma 2, you reach a reward or get update the Q values minus zero point 0.5. Similarly, if you move from 2 comma 3 to 2 comma 4, you will again get a q value of minus zero point 0.5. Here it is going from 2 comma 3 to 2 comma 4. It is not going to go left, because if it will go left, it will see a reward of minus zero point 0.5. But if it is going to go up, down, or right, it will get a reward of 0. So obviously 0 is greater than minus zero point 0.5. That is why it is going to look into the q value and take that particular decision. So as we proceed, these q values keep on updating with time. Yeah, moving back here, so we update the previous value. Again, in the subsequent move, as your random value declines, or your as your epsilon basically declines, you will be making moves with respect to the queues. Or for instance, if you have two possible moves, you are going to obtain its indexes. You in the queue, you are going to check which position, which index is basically giving me the highest reward. That becomes your best move index, and that is the move that you choose. So the inner loop will execute 10,000 divided by 200, which is 250 times, and it will keep on attempting the paths. Out of those 250, maybe 200 times it reaches the destination. So those become your valid paths. And yeah, out of those valid paths, you are going to choose one path which is the shortest. That becomes your current best. Now you compare it with the outer loop, which is your learning steps. So here, if your current best path in the inner loop, if it is lesser, or it has a length which is lesser than the best path already available, then you update the complete or the best path. So this way we complete the program, and we obtain towards the end, we just the best path becomes more of a static path, because now the robot has gained sufficient information or has updated the queue completely, and it will just keep on taking that path. So here, if we see further, we have updated the Q value like this. This is the final Q table that we have. So if you are in position 0 comma 0, you will be looking for one of the moves. So up, down, left, right. As we see, maximum value is available here. You will be taking right. This is up, this is down, left, and right. So on this value basis, it calculates. We are printing some of the best moves. So these are arranged in the descending order, like 7th, 6th, 5th. So at the end, we will see the best move. So here, steps taken 33. The again from 33, it improved to 29, and again it will improve to 25. So this is the improvement because of the cues it is taking. And then 23, as you will see, this queue or the maximum the steps taken to reach the destination will keep on decreasing as the queues are getting updated, queue values are getting updated. So from 23 to 21. So this is the least possible value which is required to move from destination to the source to destination. Now let's look how it gets updated. For instance, here this is the final q value that we have taken. And here, if you see, imagine like since in the beginning we are at state 0 comma 0, and the possible values for 0 comma 0 are up, down, left, right. So from these, we will be taking maximum is 4.8. You will take the max. So 4.8 is it taking us to the right. So from 0, 0, you will be taking right. You will reach here. Yeah. Now, since you have reached 0, comma 1, from 0, comma 1, you have to decide. So this is the grid for like value for 0, comma 1. Again, we see 6.51, which is indicating right is the maximum. Again, you take right. You reach 0, comma 2. From 0, comma 2, if you see, you have maximum value of 8.3, which is indicating down. So from here, you will take down. So this way, if we will just follow the Q table, that will give us the quickest way to reach the destination. There are chances or 10% of the moves in this approach will be random and rest will be dynamic or not dynamic, basically taken on the of q would be exploited or the greedy moves. So this is how epsilon greedy works in Monte Carlo. Thank you.